Hello, everyone. Thanks for coming to the last session on the last day. This is the victory lap session. I know it's been a long 3 days, but thanks for joining. Before I get started, I have an announcement, I guess. So we're going to be raffling off this Amazon Echo at the end of the session. If you have a ticket, hold on to it. I've been instructed to say that if you wear your Cloudera t-shirt, that one over there, you get a second ticket. So they'll come around and give a second ticket at the end of the talk, and then we'll raffle. Oh, and everyone doesn't have a ticket, just come put up your hand and you'll get one. Awesome. Everyone's hand should just go up, right? Okay, so so my name's Costa. I work at Cloudera. I'm the tech lead manager there on the Spark team at Cloudera. I've previously contributed to Spark, but that's been a long time ago. And before that, I was working on Cloudera Manager. And today, we're going to talk about Spark and how and some of the things that come up when running on a multi-tenant cluster. So before I get started, who here is like an administrator on a cluster, like administers clusters? Okay. And who here is like a Spark developer who builds Spark applications? Okay, great. And how many of you use multi-tenant clusters versus like single-purpose, one-off clusters? Okay, cool. And how many of you have Spark applications in production? Wow. Okay, that's more than I thought. Okay, cool. That's good to know. So there's a number of challenges when running on a multi-tenant cluster, and I'm just going to go over a few of the interesting challenges and things that we have noticed from our customers. This is obviously a biased set of items, and I can't cover everything in 40 minutes. So because I decided what we're going to talk about, I chose the list. But what we'll talk about is sort of how to, one of the important things is determining like a predictable execution time for your Spark applications, right? So if you have like your own cluster, you have full control of that cluster and you run your Spark job whenever you want, or any other Spark jobs whenever you want, and you have full control. But when you have a multi-tenant cluster, how do we ensure that some jobs don't get starved out from other jobs? And how do we have like different priorities on different jobs? Next, we'll talk about cluster utilization. This is actually pretty important for Spark because Spark likes to hog a lot of resources by default. I'll talk a little bit about security. Security is a whole other conversation, but I'll just talk about the the more interesting aspects with regard to security when it comes to multi-tenant clusters. And then I'll also talk about a little bit about configuration management and some of the challenges when you have multiple users trying to submit jobs on a shared resource. Okay, so to solve the first problem, which is how do we deal with resource management when it comes to Spark, I'm going to talk about Spark on Yarn. This is the cluster manager that we know the best. There is also Spark on Mesos. I don't know too much about Spark on Mesos, but I can talk about Spark on Yarn. And then there's standalone mode. Who here uses standalone mode? Okay. Who here uses Spark on Yarn? Okay, great. Okay. So why Yarn? So originally when we started working on this, we chose Yarn just because it has a pretty mature resource manager. It integrates well with Hadoop. Because there was already security between Yarn, Node Manager, and Resource Manager, adding security to Spark became possible. And the Spark on Yarn project, the module inside of Spark on Yarn, is pretty mature and has an active community. And we've been contributing to that and fixing issues with the Spark on Yarn project. Cool. And there's a lot of other reasons to use Yarn or compared to other resource managers. This isn't so much like a conversation about that. It's more about running Spark inside of your Yarn cluster. So how do we run a Spark job inside of Yarn? Really simple. You just specify that you want to run it on Yarn. You have a few other parameters. This is just a small subset. So you specify the number of executors, the number of cores, the amount of memory in your class. There's, same with standalone mode, there's also a Yarn client mode. We'll talk about that in a little bit. But here we're running it in Yarn cluster mode. OK, so how does this work? So we'll talk a little bit about how Spark on Yarn works. So we have a few machines. We have 3 machines. And these 3 machines talk to each other, obviously. So Yarn has a resource manager, and then node managers that run on each one of these machines. And typically, there's 1 node manager per machine. And the resource manager could be on its own machine or co-located with another node manager. Cool. So to simplify, let's assume that all the jobs that we want to run are going to specify the same number of cores and the same amount of memory. So you can sort of conceptually think about these like slots that we have that we can execute our jobs in. So when we run the Spark command that I had just shown, we create an application master on one of these machines under a node manager. And then previously, we showed that we wanted 3 executors. So Yarn creates for us 3 containers. And then the driver runs in the app master in cluster mode. And the executors run on all the containers. Pretty simple. Now, let's say someone else came along and they ran their job well. Another application master gets created, in this case, on host B. According to this diagram, that job only requested 2 executors. So there's 2 containers that get allocated on the node manager. And Yarn figures out where we should allocate these containers based on resources. And so these happen to be on host C. And the driver happens to be on host B. So what are some gotchas when you're using Spark on Yarn? And these are some of the things that we've sort of ran into. So Spark you can specify in Spark, how big you want your executors to be, and how big you want, how many cores you want per executor. But that all has to line up with the configuration that you've set up in Yarn. And sometimes the people who have set up Yarn are not the people who are also running Spark. So you have to make sure that if your node manager, the maximum memory that your node manager has, is 5 gigabytes, you can't allocate a container that's more than 5 gigabytes. Not even so. I mean, there's also a per container maximum on cores and memory also. So there are safeguards that administrators have, and you just have to make sure that you're working within those boundaries that the administrators have set up. Another one that is one of our favorites is the overhead memory that you have to set up. So by default, when you launch your job and you say, I want my executor to have 5 gigabytes, what really is going on is it's requesting from Yarn more than 5 gigabytes. It's adding on 10% for what is called like the overhead, which is to account for the JVM overhead, some direct buffer allocations that you're doing, off heap, things like that. And it's requesting from Yarn, let's say on 10%, so it's requesting 5.5 gigabytes, if my math's right. Yeah. Yes. And if your application starts allocating more memory than that, meaning like let's say you're using something like Snappy or you're using a native library and you start allocating more memory, Yarn will kill you. And it is pretty aggressive about that. And there's no real way. We've been talking to the Yarn team about creating this concept of like soft limits. So if there is actually memory available and the machine is not under constraint to allow the containers to continue running, something like the C group, sort of how C groups have soft memory limits and hard memory limits. But that's not in yet, and you have to be aware of this. So if you're not, you're going to see a nice little error like this, which says something like, your usage has exceeded. So in this case, we've specified that we can only go up to 2 gigabytes, but we're using 2.1 gigabytes, and we've exceeded the amount of memory. So you see these in node manager logs a lot. if you go over, and all of a sudden, and actually since Spark, I believe 1.4 or 1.5, these messages also bubble up in the driver logs. But before that, you actually had to go into the node manager logs to see that. All you'd see is like lost communication with executor in the driver logs. Cool. So let's go back to our example. And what happens here when another job comes and tries to allocate, tries to say, hey, I actually want to run on this cluster? Well, it's requesting 3 executors, but there's only availability for 2. And by default, if you run this, what will happen is Yarn will give you the 2 resources, but then you don't get your 3rd resource until resources are freed up. So this is OK, except in situations where you actually want to have some guarantees for your jobs. So basically, the real question is like, how do we share this common resource? Well, Yarn has the ability to create like resource queues, and you can set priorities on those resource queues. So you can say that, hey, I want to create a resource queue. I want to create a pool that is for, say, development, and then I want one for production. And then when you submit your job, you can submit that job to that specific resource pool. And there's also security around those. So like not anyone can submit to that resource pool. You have to have permission to submit to that resource pool. There's also a concept of preemption in Yarn, and preemption says that if you enable preemption, if you have a Spark job that's running and it's running and the cluster is at full capacity, another job comes in and is submitting on a higher priority queue, Yarn will go and just whack like your containers. And this was actually a problem in Spark. Well, there were a number of issues in Spark, but a major one was fixed in Spark 1.6. So if you're using preemption in Yarn, make sure you are using Spark 1.6 and higher. But because even though this problem has been fixed, if you're doing things like caching, you could actually end up creating this like you can kind of do this cataclysmic like failure because you're under pressure. You lose a machine that has a cache. Let's say you're using Spark caching. You have to now go and like recompute the cache values, and not even just the cache values, also the shuffle data that lives on that machine. That adds more stress. And then you could, as the job is trying to get more and more resources, the job that is currently trying to like do like recomputations could end up failing and running out of memory because the partitions are getting bigger and bigger and bigger that you're trying to process on fewer and fewer machines. And Spark doesn't like dealing with large partitions. So this is how you could specify the queue inside of your job when you're launching your job. You just say my queue --queue and you specify your queue. By default, it uses the default queue, and then you can specify your own queue in this situation. Okay, so let's talk about locality. Locality is important when you're running on a multi-tenant cluster that has data that lives also on that multi-tenant cluster. So we could have multi-tenancy where we have data that's remote. So we have like one cluster that, let's say, is running in AWS, and you have one large cluster, and you're doing like you're running all your jobs there, but all the data lives in S3. Or you can have a cluster where you have like HDFS, and you're running all your jobs on the HDFS cluster, and you really care about locality in that case, especially if you don't have a beefy network. Okay, so let's get into a little bit about how Spark breaks down our jobs into what actually runs on the cluster, and then we'll talk about locality. So in Spark, we have a driver, we have an executor, we can actually have multiple executors. And these executors communicate with the driver. And within the driver, we have our Spark context. The Spark context holds references to our jobs, right? And then from the Spark context, we have a reference to what's called the day scheduler. And the day scheduler takes our jobs, breaks us down into stages, right? It looks through the program and figures out where the wide dependencies are, creates stage boundaries, keeps this all intact in the day scheduler. And then there's also a task scheduler, which takes each individual one of those stages and breaks it down into individual work. The work that it breaks it down in are called tasks. And a task, you can think of computation that is coupled with a partition, right? What data you're running across, and then what operations you're running on that data. So ideally, what we want is we want the task to be run on a machine that has the data. Otherwise, we're going to have to remotely read the data from a different machine in the cluster. So on the executor, each executor has a core. Actually, could have multiple cores, and each one of these tasks. My fancy animation. Each one of these tasks runs on one of the cores and can read shuffle data, can write shuffle data, sometimes. So sometimes it's reading directly from HDFS. This is why it's a dotted line. And then sometimes it's writing out to, let's say, HDFS or something else. But in between stages, it's reading and writing from shuffles, right? So like I said, we want locality ideally in both shuffles. So when we're reading like our shuffle data from before, we want that to land we want the task to read the data from the same shuffle location. And then if we're reading from HDFS, we want to read the data locally to HDFS. So let's look at our previous diagram. And let's add in here another variable to the mix, HDFS. So our application, let's say, is reading from this file X. And we have a block. So this file is broken down into, let's say, 3 blocks. So we have block 1 is replicated twice, and each one of these, one in host A and another in host B. Another block is on another one in host A, and let's say it's in host C, and block 3 is in these 2 machines. And just for completeness, let's say we have another file. It's sort of the same thing, right? And in this case, we have 3 blocks for each one of these files with a replication factor of 2. Great. So we run our Spark job, and like before, and we say, okay, we have these 2 executors, and Yarn. What happens is Yarn will launch when you do Spark submit. It will create the Spark context, and while it's creating the Spark context, the Spark will communicate with the resource manager to get the containers allocated, and then run executors on those. And if you happen, in this case, to say, we're reading data from file X. OK, well, there's an executor on host A, and there's an executor on host B. Spark is actually, when it does the task schedulings, it actually knows, oh, look, I know that I'm about to run task A that has to access block 1. Therefore, I'm going to get my task to run on host A, on the executor that's on host A. And in this situation, we're great because we can actually allocate all of our tasks on executors that are local on the machines. Well, if you rerun this application, it could end up that the executor runs on this machine, or it could have been on the other machine, but it could be on a different machine. And in this case, when you go and you actually process that Spark job, block 3 in this case will have to be remotely read, right? So that's a problem if you care about locality. And the important thing here is Spark creates the executors before it executes your code. So there's no way that Spark can know where to actually go and allocate the executors, because it's allocating that ahead of time before it's actually running your Spark application. So unless you're running an executor on every single one of your machines, there's no way to guarantee that you will actually get the best data locality. OK. And we'll revisit locality in a second. But first, let's talk about underutilized clusters. So Spark on Yarn was the first cluster manager to introduce dynamic allocation. This was added in Spark 1.4, I believe, but really shouldn't be used until Spark 1.5. There was some issues in Spark 1.4. And what dynamic allocation allows you to do is to remove the need for this num executors. And, oh yes, it was first supported in Spark CDH5.4. It allows you to remove this num executors, and Spark will create executors on demand. Right? So let's look at this example, or let's look at our diagram again. So let's say that we have these hosts, and we have these tasks, and we have these two executors. So we start processing. The task schedule says, OK, let me process the next task. It will put it in this executor. The next task will get added onto this executor. If at this point we're at capacity, we can't allocate any more we can't run any more tasks on any executor. So what Spark will do is it will communicate with the RM and say, hey, I need another container. And it will launch another container and run the task on that container. And while this is going on, it's looking for while that happened, when it's ready to launch the fourth task, the first one actually finished, and therefore it will put the task on the first executor. And then when this task is finished, the executor goes away. And there's configuration around all of this. Obviously, Spark loves configuration. There's configs to control all these different aspects. But that's generally how this works. And the nice thing about this is because you're running inside of your resource pool, you can actually set your configs to say, look, I'm just going to get as many resources as I'm allowed. So you can just say, I want everything. And then Yarn will make sure that within your pool, it will only give you the resources that you're allocated, right? So if you have multiple teams running and they're all using dynamic allocation, you can actually just set up your dynamic allocation to say get me everything, and then Yarn will be the police officer for that. So that's actually kind of cool. And this is actually a problem. This is actually a real problem if you're using Spark Shell, for example. We've had customers who say, oh, we have this really big cluster, and we have all these data scientists that go on and they type Spark Shell and they get a bunch of resources, and then their lunch arrives and they leave, and the cluster is just has just empty it just has executors that are sitting there doing nothing. And admins have set up these scripts that go around and check utilization and start killing executors, and it's just terrible. So this actually solves that problem where you can set up dynamic allocation. In that case, your Spark Shell will just all the resources will go away, and then once you start typing some code and click enter, you start allocating more executors. So here's some of the configuration, the more relevant configuration. So you can enable it. You can set the minimum, the maximum, the initial executors. The executor idle timeout is when you want to release an executor that isn't doing anything, right? So in the previous case where we saw the third executor go away, it passed the timeout, and therefore Spark kind of reclaimed that, or gave that resource back to Yarn. There's actually a problem with dynamic allocation and caching. If you're doing caching, you really can't give up executors at that point because your executors are holding your cache. So there's a config that you can specify a timeout for the cache. So by default, I believe that timeout is 0. So that timeout is infinite, I believe. So if you do have a cache, your resources don't go away. And if you specify this timeout, let's say for 3 seconds or 10 seconds or whatever, then after 10 seconds, your nodes that are not processing any work but have cache data will start going away. Right? And there's a bunch of other configurations here too. You can take a look at the docs. And if you specify num executors, this will disable dynamic allocation. There's actually a warning that will get written out. So this is really for legacy. If you basically are saying I want this number of executors, and your admin by default has set up dynamic allocation. As it basically said, hey, the configuration for everyone has to use dynamic allocation. If you actually say num executors or the equivalent in SparkConf, it will disable dynamic allocation and just allocate the number of executors that you specified. Well, so some limitations. So you still need to specify the number of cores. You still need to specify the executor memory. And yes, and then there's the caching caveat that I had mentioned. So I like this slide because I've used this slide before, which is in the future, we will want to fix dynamic allocation so that you only specify a task size, and it eliminates these 3 variables. So all we need to know is how big is your slot, and then we can take a look. We can take a look and see, hey, how many cores do you have, and do the math for you. The nice thing about this is that this will allow heterogeneous containers, because right now you can only have homogeneous containers on Yarn. So every container has to have the number of cores that you specified. So if you're talking about maximum, resource utilization, let's say that you have a cluster and there's, you have 3 cores available in every single one of the machines, but you only said you want your executors to have 4 cores, then you're kind of out of luck. Ideally, you could just say, like, just give me however many cores I can get up to a limit, and then Yarn will just create a container on that machine that has 3 cores available. So by doing it this way and doing it based on task size, we can do the math, and Spark can be much more smart about it. Cool. And the nice thing is, because dynamic allocation happens lazily, or because allocation of executors happen lazily, the locality issue that I just described 10 minutes ago goes away, because when you start running your job, Yarn will take a hint, like it knows what job you're running, so therefore it will go and allocate executors on those machines, and then Spark internally will do its second level of locality, right? So again, because like this is happening like as your job is running, so Yarn has that, or Spark has that information. That's one of the nice things. So security. Security becomes important on a multi-tenant cluster because you have shared data, most likely, and this is because like you're all using like the same cluster, right? So security has many facets. There's we can talk about encryption, we can talk about authentication, authorization, and the one that I'm going to just talk briefly about is encryption, because authentication, yeah, I use Kerberos, that's great, and authorization, that's really not that. It's really not that relevant to multi-tenant clusters. It's more about like if you're setting up ACLs for your data. It is interesting, but not for this sort of conversation. So let's talk about encryption. So encryption requires us to talk about like Spark data flows, right? So Spark has many communicates with different pieces of the system in different ways. So we have our control plane where the driver talks to the executors, and this is where it tells the executors what to do. There's also the file distribution mechanism where if you have like a jar file and you want to distribute that jar file to the executors, there's file distribution. And then the executors speak to each other and read shuffle blocks. And then there's spill data that it reads from. And there's also a UI. So all these different mechanisms, if you care about on-disk encryption and over-the-wire encryption, all of these need to be encrypted. And conveniently, for a while, Spark had different ways of communicating. Like all these different channels had different ways that spoke. So before this has been slowly getting better and better. Prior to 1.6, if you wanted to do encryption on the control plane, you had to use SSL because the control plane was done through Akka RPC. File distribution was an HTTP server, so you could like have SSL on the driver. You can have a certificate on the driver. Blocks were you use SASL encryption because I was using the Netty library. The UI, no encryption, and then spill blocks, you had to use something like EncryptFS or some other like block level like encryption because there was nothing inside of Spark. So SSL, and this is where the interesting part happens with multi-tenant clusters. SSL is just a real pain to configure because on a multi-tenant cluster, you need to have different certificates for different users distributed on the cluster. So every user has to have their own certificate because you don't want to share certificates between users because that defies the purpose of using like encryption. So you need to manage certificates around, right? Because a Spark job doesn't run as a protected user like all these other like Hadoop services. So the job runs as that user. So that user has to have access to the certificate. And so in 1.6 and beyond, there's been significant work to replace a lot of these communication mechanisms with a single common Netty networking library that uses SASL encryption. But the web UI still has no encryption or authentication. It's sort of okay because there's not a lot of sensitive data in the web UI. The shuffle and spilled blocks still require file level, like block level encryption. And another issue is that SASL in the JVM is really slow, and it also uses triple DES by default, and it's not very strong if you really care. In 2.0, the REPL, so the class distribution is also going to be using the same transport library, so that will be with SASL. HTTPS support will be added to WebUI. Again, you have the distribution of the certificate issue because the WebUI could be running anywhere on the driver. The driver could be running anywhere on the cluster, so you have to have like all your certificates distributed out. And spilling to disk is almost there. It's not going to make 2.0, and this is because we're depending on this third-party library called Chimera, which was built by Intel. And the Intel team is moving Chimera to Apache Commons. It's going to be Apache Commons Encrypt, I believe. And that has AES encryption. It's similar code to what was in HDFS. And then with that, we'll be able to encrypt on disk all the spill data, and also use that same library to do over-the-wire encryption. Instead of using the triple DES encryption, we can use Chimera to give us AES. Okay. So lastly, I want to talk about gateways, and this is something that admins talk to us about, and it has to do with how do different users who log on or want to run jobs on a cluster do this with Spark. So taking our previous diagram, we need to add a different box here, and let's call this the gateway machine. And the gateway machine is running our client, right? So this is the machine that we actually launch our job in. And this machine requires us, doesn't necessarily, but I'll get into it in a second, requires us to have a Spark installation. We need to have the client configuration so that the client knows how to talk to Yarn when it launches the job. We need to have a bunch of like random ports open because if we're running the driver on the client, the driver needs to connect to all the different executors, and it uses like different ports. And so what we need to do with this machine also is to have open up SSH. So, you guys have probably seen this. You have to SSH onto a machine. That machine is all configured and ready to like submit jobs, and from there you submit your jobs. Well, some of the problems with this is that these hosts, these gateway machines, have to be actively managed by the administrator because the machines have to have up-to-date client configurations. Like if you change the location of your resource, if you change the location of the RM, you need to know about that in the client configs when you submit a job to Yarn. Users also need to be able to tunnel. We also need to be able to, it's not really accurate, but users need to be able to SSH onto the machine and actually run their job, right? And this makes it really difficult to just have people just submit jobs from their laptops or on machines that are not part of the cluster or firewalled away. You actually have to have access to that machine. So some security-conscious administrators who don't want just random people SSHing onto machines, that those machines then have open ports onto a bunch of their machines on the cluster, that you can't really work around this. Yarn does allow different versions, and this is where I was saying that you don't necessarily need a Spark installation. Yarn does allow different versions of Spark to run at the same time, but Spark doesn't deal well with different versions if you have some shared services, and practically you do. So in our little diagram here, really what's missing is you have a history service, and if you're using dynamic that's messed up. Okay, if you're using dynamic allocation, you also have a shuffle service that's running inside of the node manager, which is handling your shuffling. And if you're running different versions of Spark, and those different versions of Spark are running to the same location of the history server, the history server can only really read like older events. An old history server can't read new events. So you're not going to be able to have like a newer version of Spark running on the cluster and still be able to see all your information on the history server. You'd have to actually you have to do some configuration to specify that you want to write events in a different location for your Spark job. The shuffle service, there's been a lot of work to try to make it so that it's compatible between even Spark 1.x and 2.0, but there could be issues where it won't be compatible with the version that you're running. So in reality, administrators just say, this is the version of Spark that you're running, at least in our experience, and then users just use that version, right? So that's why you really do need to have the Spark installation that's managed by the user. So an alternative to this, and this is like a shameless plug here, but there's this open source project that we've been working on. It's called Livy. It's a REST service that allows you to, that manages long-running contexts. So what this is Livy will sit and actually administer contexts that are running inside of the cluster, so remote contexts. And this, the Livy and the cluster itself can be managed, and the client could submit jobs directly to the REST service, and that can be behind HTTP and also protected by a firewall. So there's a few different use cases, but you can use Livy, for example, to just do a curl and submit my job to the cluster, and it will just go and run that job. So from your laptop, you can just say hey, I just want to run this job on the cluster, and I don't need to have a Spark installation, any client configs. All I need to know is the port and host name of Livy, and it can go and submit the Spark job. And so one of the problems here is, how, and this now goes beyond just submitting Spark jobs, right? Now it goes into how can we actually have programmatic access to our jobs that are running. So Livy also has a client, and this client allows you to have long-running Spark context and programmatically submit jobs to that long-running context. So you can, as a client, say, hey, I launch a context that's running, I submit a bunch of jobs, I submit my job, I get results back, I submit another job, I get results back. Another client connects to the same context and submits jobs to that context. If we're caching data, they can share the cache, things like that. The nice thing about Livy is that the driver is not running inside of Livy. So Livy is actually a very lightweight web service that is using Yarn cluster mode. So it's only controlling drivers that are running inside of the cluster. So the first version is just had a Java API, but there's also just recently submitted a Scala API. But this is sort of how it would work. You create the Livy client. You submit in Java 7, we don't really have nice closures, but you submit your job. You sort of block, and then you close your client. And then the job itself, you just have access to the context. In reality, what happens here is that no Spark code is running on your client. All it is you have access, you have a build dependency on Spark core, and you're running you're writing Spark code. So here you can see you just have access to the Spark context, and you just write your standard Spark code, and then that closure gets serialized and sent over to the cluster, and the cluster is what runs the code, right? So there's no Spark running on your machine. This is an open source project. It's Apache licensed. You can check out the website. The code is here. Contributions welcome. It's we just had the first upstream release, so it's brand new. But this might help if you're concerned about people accessing, actually launching jobs on the cluster. That's it. Ooh, okay. Anyone have any questions?
Would you say dynamic allocation is robust enough to run in production? And how would the log aggregation work on the executors that are terminated?
Right. So the question is dynamic allocation robust enough to run in production, and how does log aggregation work? So in terms of, is it robust enough? There are bugs, and there isn't any big outstanding bugs that I would say don't use dynamic allocation. It's been around since Spark 1.4, and so we've been continuously trying to improve it. We have customers who are using it in production, but there are some bugs. I can't say it's bug free, right? But I wouldn't say don't use it in production. In terms of log aggregation, it's a good question. I don't know. Actually, I don't know if you get access to those executors once the logs from those executors once they go away. That's actually a good question. you can give it a try. Anyone else have a question? Yeah.
If you're using Spark Thrift Server and connecting to a Sigma JDBC to a Tableau, what we have seen is, Spark Thrift Server just uses one of the containers assigned to it, and all the jobs, all the executors, like they're running within that container. Is there a way to control, how Spark Thrift Server behaves in order to scale it out?
Right. So the question is around Spark Thrift Server and the fact that the Spark Thrift Server just runs one context that multiplexes requests coming in. I don't know of a way to get around that. That's part of one of the big issues with the Thrift Server right now, which is you have this context that's shared between all users. In addition, security becomes a problem, right? Because you want to have users that come in and you want impersonation, for example. So if you're connecting as like user Costa, you want the jobs to run as user Costa, and Thrift Server doesn't do that. There's a number of problems, a number of limitations, let me say, with the existing design of the Thrift Server, and I don't know of any good workarounds around that.
Will Livy solve that problem? Like, you provide a JDBC layer on top of it?
Yeah. So we've been that has been thought of. Like we've been talking about that, which is, hey, what if one idea, and this is like a very half-baked idea, but one idea is, hey, what if we run a multiple thrift servers inside of Livy, and therefore those thrift servers are running as the users that you care about, and then you can connect to those thrift servers. So you have basically like micro thrift servers that you connect to, and they're running as you, and they scale out to whatever you need them to be used at. There's ideas like that. Yeah, there's something that we can do there. We haven't really explored it too well. I think I'm like a minute and a half over. If you guys have any more questions, come grab me after. Thank you. Oh, yes. And we're going to raffle this. Oh, yeah, whoever's running their Cloudera shirt gets a double one. I think there's one over there, right? Yes, there's one over there.